Welcome back to the Explainer. Today, we're diving straight into the elegance of the linear function. Specifically, we're going to look at how a seemingly abstract mathematical equation magically transforms into a perfectly understandable visual straight line. We're going to break down the anatomy of a line, piece by manageable piece, using our source material to completely demystify this foundational concept. Here's our game plan for today. First, we'll meet the linear function. Then, we'll decode the slope, find the intercepts, and finally, put graphing in action. All right, part 1. Meet the linear function, the basics. So what is it exactly? Well, at its core, a linear function is all about a constant rate of change. That phrase right there is the secret sauce for everything we're about to discuss. Because that rate of change never wavers, it doesn't speed up and it doesn't slow down, its graph is always a predictable, perfectly straight line. It's reliable, and visually, it's honestly kind of beautiful in its simplicity. And here is the master equation behind that straight line. Y equals mx plus b. You've probably seen this before. It's the slope-intercept form. Think of it like this. Every single straight line in the universe is totally determined by just two little components in this equation, the m and the b. If you know those two letters, you literally hold the genetic blueprint for the entire line. Moving right along to section 2, let's decode that slope, the m in our equation. Okay, so the m stands for slope, and slope has two very specific jobs. It measures exactly how steep a line is, and it tells us how that line behaves as we read it from left to right across a graph. I like to think of it as the steering wheel and the gas pedal combined. It completely dictates the direction and the intensity of our line. Now, mathematicians universally call this directional movement rise over run. It's a super handy, memorable shorthand. Based on our source material, the equation for this is the change in y, which is the vertical change, or the rise, divided by the change in x, the horizontal movement, or the run. Basically, you rise up or down and you run left or right. You're simply building a staircase for your line. So that staircase can take 4 distinct visual directions. Let's walk through them. First up, positive slope. This is where the line physically rises as your eyes move to the right. Second, negative slope. It falls as you look to the right. Third is a zero slope, which just creates a perfectly flat horizontal line. And finally, the fourth type is an undefined slope. This creates a vertical line, straight up and down. And actually, here's a fascinating little detail, straight from the textbooks. A completely vertical line is actually not a function at all. It entirely breaks the rules of what a function is allowed to be. Pretty wild, right? All right, section 3, finding the intercepts, or the b in our equation. Now we've got the b isolated from our master equation. This represents the y-intercept. Mathematically, it's just the value of the function when x is exactly 0. But visually, it's the exact spot, point 0, b, where our straight line slices right through that vertical y-axis. This is our starting dot. Before we can build our staircase using the slope, we have to know where the very first step lands, and the y-intercept gives us that exact anchor point. Just to be totally thorough, our sources do point out that a line can also have an x-intercept. This is exactly what it sounds like. It's where the line crosses the horizontal x-axis, meaning y is exactly 0 at that point. But for standard graphing and algebraic modeling, the y-intercept is absolutely your go-to. 9 times out of 10, it's the one you're going to use first when graphing a line. And that brings us to section 4, graphing in action. Let's bring it all together. Let's look at an actual real-world example straight from our source material. We're going to graph the equation y equals 2x plus 1. Just looking at those numbers, the 2 is in that m position, right? So that's our slope. The 1 is in the b position, making it our y-intercept. Let's see how these specific variables literally translate into a drawing. Okay, step 1. We look at our b, which is 1. We plot our very first point on the vertical y-axis right at 0, 1. Boom, anchor dropped. Step 2, we use our m, our slope, which is 2. Now, remember rise over run? A whole number 2 is functionally just 2 over 1. So, from our anchor point, we just go up 2 spaces and to the right 1 space and plot our second dot. Step 3, draw a straight line directly through those 2 points. And there you go, you just successfully graphed a linear function. This breakdown really beautifully illustrates how these manageable, bite-sized pieces come directly from structured, reliable mathematical principles. Our source material from Western University and OpenStax compiles these exact definitions of slope and intercept that we just walked through. It really proves that whether you're analyzing a dense academic text or just sketching out a quick graph, the fundamental anatomy of a line never changes. The slope always dictates the rise and run. The intercept always drops the anchor. And that constant rate of change always delivers that perfect straight line. So we've mapped out the math on the page, but here's the thing. These principles are literally everywhere. A linear function is really just a constant rate of change. So what everyday things in your world follow that rule? Is it your hourly wage at work? Maybe it's the steady drain of your phone battery while you're watching this, or the predictable cost of buying apples by the pound. The next time you see something moving or growing at a perfectly steady pace, I want you to picture the slope, picture the intercept, and realize you are watching a linear function play out in real time. Keep observing, keep questioning, and we'll see you on the next explainer.